Hello, magandang araw. Welcome sa aking YouTube channel. Sa mga bago lang, ako nga pala si Bartolome Alaba. Isa akong licensed civil engineer. And in this video, I am going to talk about response spectrum analysis. So guys, stay tuned. Watch the whole video. Actually, there are three procedures to perform seismic analysis. One is equivalent lateral force procedure. Second is seismic response spectrum method. And the other is the time history method. And this time history method is the rigorous dynamic method analysis and most accurate method among the three. Well, response spectrum and time history are under the category of dynamic analysis procedure. And the equivalent lateral force is for the static force procedure. Time history method can perform both linear and non-linear analysis, while the response spectrum analysis does only the linear analysis. For the equivalent lateral force procedure, it is commonly used for ordinary and regular structures. I have videos regarding how static analysis is performed. So this time, I'm going to move forward to discuss the response spectrum method of analysis. Response spectrum method is an iterative procedure, and it uses response spectrum curve to do the calculation of seismic demand in any structure under consideration. What is this response spectrum curve, by the way? A response spectrum curve is a jog plot of peak or steady-state response by series of oscillators of varying natural frequency that are forced into motion by the same base vibration or shock. The resulting plot can then be used to pick up the response of any linear system, given its natural frequency of oscillation. So, it is being said that if I have different oscillators in here with different time period, so if I have to apply force at the base to each of this single degree of freedom oscillator, I'll get the peak response of each of this oscillator and record it by plotting a graph. So in the graph, acceleration response in the vertical versus time period in the horizontal. The graph will look like this. And this graph can then be used to check the response of another structure by using the period of that structure and project it here. And this will be the response of that new structure. And we notice in this graph, this is not a smooth graph, and indeed, this is the jog plot of responses of these oscillators. And in the previous recorded earthquake, like the popular El Centro earthquake, which was happened last May 18, 1940, at the Imperial Valley, Southern California, where the magnitude was 6.9, the response spectra of that earthquake looks like this. So the actual response spectrum is not smooth. It is a jog plot of peak responses. Ang response ay zigzag, kagaya nitong pinapakita kong sa El Centro earthquake event. May response na mataas, tapos ang kasunod ay biglang mababa. And so on. Random ang mga points. Bawat earthquake na nangyayari sa kahit saang lugar ay may iba-iba ang response spectrum curve. So ang tanong is, anong response spectrum curve ang gagamitin to analyze and design structure? Bawat building code ay gumawa ng smooth response spectra specific para sa isang lugar. So kagaya ng UBC 97 code example, ay gumawa sila ng response spectrum envelope na kung saan para tawagin ito na the design response spectrum. At ito ang maaaring gamitin ng mga engineer to design future buildings. to resist future earthquakes in a certain place, at ito ay adopted ng NSAP, National Structural Code of the Philippines. At hanggang ngayon, ito pa rin ang ginagamit natin dito sa Philippines. Itong smooth design response spectrum ay naka-base lang din yan sa previous earthquakes na nangyayari na sa isang lugar, at naka-base din sa soil classification. So kung titingnan natin ang NAACP code section 208.5.3.2 sa figure 208-3, yan pa yung response spectra na galing kay UBC 1997. Ang spectral acceleration dito sa graph na ito is a function of soil strength. So kung makikita natin dyan, ang bawat lugar sa Pilipinas ay may iba-ibang CE value. So bawat pagbabago ng CE value ay may pagbabago din sa response spectrum curve. So makikita ninyo ang CE values ay makikita sa NSAP table 208-7. Additionally, itong spectral acceleration, bukod sa function siya ng soil strength, function din siya ng damping coefficient. So kung magbabago ang damping coefficient dito, magbabago din ang spectrum graph. So in other words, for simplicity mga guys, the response spectrum analysis procedure is done by deriving the dynamic equation of motion of a single degree of freedom structure. Like for example, kung meron tayong simple structure dito, ganito. Itong structure na ito has inherent properties like mass, tawagin na natin M, mass M. And then it has stiffness K. It has also a damping force that dissipates energy, and let us call the damping constant as C. So kung itong structure is subjected to ground acceleration here, and let us denote this ground acceleration as negative mu double dot g of t. So ito yung earthquake force. So kung subjected na itong structure, of course the structure will respond. At anong mga forces na inherent sa structure to react to the external force, which is earthquake? So ano-ano yung mga yun? Una, itong inertial force na let us say mu double that of t. Of t kasi ano siya, dynamic force eh. U double that means acceleration. Then ang second is the damping force, Cu dot of t. So U dot means the velocity. Next is force due to stiffness. So Ku of t. U means displacement. And all equal to negative mu double dot g of t. So remember, negative mu double dot g of t is the ground acceleration or the earthquake force applied to this structure. So to rewrite the dynamic equation of motion for a single degree of freedom structure, the equation is mu double dot of t plus cu dot of t plus q of t is equal to negative mu double dot g of t. Ito yung dynamic equation of motion of a single degree of freedom structure. Now, i-relate naman natin tong C. C is equal to 2 times mass times xi times omega. Ang omega dito is the frequency. Then, yung stiffness K naman is equal to mass times omega squared. And substituting these expressions into the dynamic equation of motion, we are left with this equation. Mu double dot of t plus 2m xi omega u dot of t plus m omega squared u of t is equal to negative m u double dot g of t. So from here, from this equation, we can cancel this m. So makikita mo, makakancel natin yung m. So ang matitira na lang is u double dot of t plus 2 xi omega u dot of t plus omega squared u of t all equal to negative u double dot g of t. So ito yung earthquake demand, itong negative u double dot g of t. So ito yung kailangan natin. So para makuha natin itong earthquake demand or earthquake force, ito, to get the value, kailangan lang natin ang mga values na nasa left side ng equation, kagaya ng xi and omega. Which is, itong omega naman ay frequency yan. Reciprocal lang ng time period. At ang time period ay makikita na yan sa structure. Itong xi ay related lang ito sa damping coefficient, which is, karamihan naman ang ginagamit ay nag-a-assume lang tayo mostly ng 5%. So, dyan kinukuha ang equation ng response spectrum analysis. So, balik tayo sa single degree of freedom structure natin. So, di ba, nag-apply tayo ng external force, which is the ground acceleration dito. So, may movement yan in this direction and in the orthogonal direction. The force or the structure will be displaced in the base. Siyempre, may movement yan. At the same time, it will have a deflection at the top. So, kung titingnan mo, magkakaroon siya ng deflected shape like a cantilever structure. This shape is called the mode shape. Ito yung mode shape ng ating structure ng single degree of freedom. Ito yung one mode shape niya sa x direction, ganun din sa other direction, sa g direction. Every mode shape ay may one natural time period. So, itong deflection na ito, kung i-multiply natin yan sa stiffness ng structure, we will get the shear force. Na kung saan itong shear force, yun ang kailangan sa design. And remember, known yung mass ng structure natin. Kasi, pag nag-design tayo, siyempre may mga sizes na yan. So, makukuha ang mass. So, kung ang shear force ay i-divide natin sa mass, then we will get the acceleration. So, di ba, basically, kagaya ng nabanggit natin kaya na response spectrum analysis uses response spectrum curve. Dito sa spectrum curve, kunin lang natin yung time period, i-project natin vertically, makukuha ng acceleration response. So, kuha na rin ang shear force. Ito ang pamamaraan sa single degree of freedom structure. Paano naman kung ang structure mo ay multi-degree of freedom structure? Remember, single degree of freedom structure has only one mode shape in its direction. How about the multi-degree of freedom structure? Sa multi-degree of freedom structure, the number of degrees of freedom is equivalent to the number of modes. So, imagine niyo itong structure na ito. Ito ay isang multi-degree of freedom structure. So, kung gagamitin natin itong staad software na ito para hindi tayo mahirapan, kwentahin kung ilang degrees of freedom ito, makikita dito sa output. Punta lang tayo sa analysis output. Then, sa floor diaphragm, then scroll down. Then, ito na yung total degrees of freedom. Meron siyang 5,430. So, kung 5,430 degrees of freedom, ibig sabihin yan, meron din siyang 5,430 mode shapes. Ganun siya karami. So, kung ganun karami ang modes, paano makakalculate ang base shear sa structure na ito? So, kung paano kinakalculate ang base shear sa single degree of freedom structure, kagaya nung pinakita natin kanina, ang binanggit ko sa inyo kanina, ay ganun din ang ginagawa sa multi-degree of freedom structure. Ang una nga lang dyan ay kino-convert muna ang multi-degree of freedom structure into a number of single degree of freedom structure. So, parang kung mayroon kang marami kang mga maraming moods yan. So maiisip po parang ang dami niyang single degree of freedom sa structure na yan. Tapos yung moods na yan, isa-isahin sa pag-calculate. So ang response spectrum analysis ay tinatawag na modal analysis dahil ginagamit sa analysis na ito ang bawat mood shape ng structure to calculate the individual forces ng bawat mood shape. So one mood shape, one force. So kung merong 5,430 mood shapes sa isang structure kagaya nito, meron din siyang 5,400 forces to be calculated. So ang dami niyan. However, kung mag-design tayo ng mas mataas na structure, mas marami ang number of moods. So magiging tedious at matagal ang analysis. Kaya ang ginagawa, pag mga multi-degree of freedom, pinipili lang yung mga moods na nagpa-participate sa vibration. Kagaya nitong sa staad file natin mga guys, meron itong 5,430 degrees of freedom. So ibig sabihin, mayroon din itong 5,430 mood shapes. Itong mga shapes na to, hindi ito lahat sinasali sa calculation. Sa staad, kung gagamit tayo ng software, ang default number of mood shapes na ginagamit doon ay 6 lang. So sa 6 na ito, tinitingnan kung aabot ito sa 90% participation factor. So kung makikita natin dito sa output, punta tayo sa participation factors. Ito. So makikita natin 6 moods lang ang ginamit ni staad. So hindi ako naglagay, kundi si staad na ang automatic na magbibigay ng 6 moods. So sa 6 moods na yan, makikita mo dito sa sum x, sum y. Sa x, ito yung, alam mo, sa mood 1, 49.015 lang ang participation. Sa mood 2, mood 3 hanggang sa 6, 82. 82 ang kanyang mood participation factor. Yan ay sa x direction. Sa z direction naman, 63.18. So ang requirement dyan is kailangan at least 90%. So kung nangyari man na ito ay 90%, kailangan both. Ano ba? 90% dito, tas 90% din dito sa Z. Meaning to say, enough na itong 6. Itong 6 modes, enough na to siya para mag-start ng mag-analyze. Ang ginagawa sa mga modes na hindi sinasama ay ginagamitan na lang ng missing mass para medyo accurate pa rin ang result. Kaso hindi siya umabot ng 90%. So dahil hindi tayo umabot, kailangan magdagdag tayo. So ang gagawin natin dito, exit tayo dito sa viewer. Punta tayo dito sa analysis and design. So, then pasok tayo sa miscellaneous commands. Then cut off mode shift. So nakikita mo, bago pa man, meron na nakalagay na 6. So, i-enter mo lang dyan. Let's say, sabihin natin, 12 modes lang muna. Huwag natin siya biglayin kasi hindi natin alam. Baka mamaya sa 12 modes, makukuha na natin yung minimum requirement. So, okay natin. So, uulit-ulitin lang ito until both X and Z direction has reached at least 90% participation factor. Dito sa sample, naglagay ako ng 40 modes kasi sa 12 modes kanina, hindi pa umabot sa 90% yung participation factor. So, makikita natin dito sa output, sa 40 modes na gamit ko, ang participation factor sa X is 94.864 and sa Z naman is 96 or 95.154. So pagkatapos nito, kinakalculate na ang forces bawat mode. At makikita natin dito sa staad output ang mga forces. So ito na yun. Mode 1 sa G. Or dito tayo sa X muna. Ito na yun. 1,328. Nakalagay ito base year in kilonewton. So along X, ito yung mga values niya. Ngayon, to get the single base year, ang gagawin lang naman dito sa mga forces na ito ay i-combine ito gamit ang CQC method. In my case, CQC ang gamit ko. So kaya naman 0 dito sa G, nandito yun sa kabilang bahagi. Dito naman siya. So kino-combine lang siya. Pwede tayong gumamit ng SRSS method at may mga ibang mga method. Pero ang most popular method is itong SRSS at CQC. So makikita dito, mayroong SRSS, mayroong 10 PCT, mayroong AVS. CQC naman ang ginamit pag ang time period mo is closely spaced. So, in my case, CQC ang gamit ko. So, ibig sabihin, sa G, ang base year niya is 1,859. Ngayon, sa X, dito sa X, ang X is 1,702.06 kilonewton. In the next video, I am going to take this sample structure and see how we got these base year values. Sa ngayon, hanggang dito lang muna tayo. Thanks a lot for watching and please don't forget to like and share this video. Sa mga bago, please don't forget to subscribe and hit the notification bell to keep yourselves updated as I keep on uploading new videos and tutorials.